Welcome to VTeach. In this session, we will be discussing about cavities, re-entrant cavities. So the term cavity always refers to a closed enclosure, and this enclosure will be either a metallic enclosure which is going to confine the entire electromagnetic energy. So the stored electrical and magnetic energies inside this cavity will be determining its equivalent inductance and capacitance, and the energy dissipated by the finite conducting or conductivity of the cavity walls determines its equivalence resistances. So why we are been using cavity is that in order to study inductance, capacitance as well as resistances. So one is, it is cavity is a metallic enclosure where you are going to capture or confine some electromagnetic energy. When we say that it is an electromagnetic energy, we will be having electrical as well as magnetic energies inside that. So this electrical and magnetic energies will be able to determine us about the inductivity and capacitivity. After that, the walls of this metallic enclosure will be acting as capacitance to us, by which we will be able to define the resistance. So this is the primary application of the cavity. Let's move on to the re-entrant cavities, where it is one of the metallic boundaries extended into the interior of the cavity. Remember, it is one in which the metallic boundaries will be extended into the interior of the cavity. Already cavity is a metallic enclosure in which we are going to again define the boundaries to it in the interior part of the cavity. And one of the most commonly used re-entrant cavity is coaxial cavity. And there are several cavities that are been there for us. So here is the diagrams that are been present here. Coaxial cavity. So this is the common cavity that we will be using for practical applications. The next one is radial cavity, and the third one is tunable cavity. Fourth one is toroidal cavity. Fifth one is butterfly cavity. These are some of the cavities conventionally they are being used, but most appropriately we will be using coaxial cavity itself for the convenience. And when it comes to the tubes, conventional tubes, as we discussed earlier, they are going to have linear tubes. That linear tubes we call it as O-type tubes. Now we are going to see cross-field tubes, that we will be calling it as M-type tubes. In this, we are going to have three separations or three categorizations. One is resonant, the other one is non-resonant, and the third one is maser effect. So these three segregations, if you observe, the first one, if resonant is been there, from there we will be moving on to standing wave, from standing wave to re-entrant, and re-entrant to magnetron. And in non-resonant, we will be having two types again, forward wave, backward wave. Again in forward wave, we will be having two types, re-entrant, non-re-entrant. In re-entrant, you are going to have forward wave cross field amplifier, whereas in non-re-entrant you are going to have dimetron. And even in backward wave non-resonant, we are going to have re-entrant, non-re-entrant, whereas in re-entrant we are going to have amplitron, whereas in non-re-entrant you are going to have carcinotron. When it comes to the maser effect, you are going to have gyrotrons. So these are the classifications of cross-field tubes, and they are being termed as M-type. And in this, what is that is, the electrical field and magnetic field are perpendicular to each other, whereas there the magnetic field is confined along with the electrical field. Here magnetic field and electrical field are perpendicular to each other. That is the reason they are considered to be as M-type tubes. And in this cross-field tubes, the electrons emitted by the cathode will be accelerated by the electric field and gain velocity, but the greater the velocity, the more their path is going to bend by the magnetic field, as it is in perpendicular, the electron beam is going to bend. So if an RF field means radio frequency field, is applied to the anode circuit, the electrons entering the circuit during the retarding field will be deaccelerated and gives up some of their energy to the RF field. Consequently, their velocity is going to get decreased, and these will slower the electrons to travel the DC electric field far enough to regain the same velocity as before. Because of these cross field interactions, only those electrons that have given up sufficient energy to the RF field can travel all the way to the anode. This phenomenon, we will be calling it as accelerated and deaccelerated phenomenon, where we will be confining only with the sufficient energy that needs to be given to retarded field, and based on that the electrons should carry their energy to move towards the anode. So in that way the M type devices will be relatively efficient. Thank you.